Continuing with the reactions of alcohols, now we are going to look at oxidations of primary alcohols. In an oxidation reaction in chemistry, specifically organic chemistry, our molecule is going to gain oxygen atoms or is going to lose hydrogen atoms. Whenever oxidation occurs in a primary alcohol, understand that it can yield an aldehyde or it can yield a carboxylic acid. Now, how do I know that my primary alcohol will yield only an aldehyde or it will yield a carboxylic acid? It depends on the type of oxidant reagent that we utilized. Typically, what we observe in this class is that oxidants, which we illustrate them as an O in brackets, can come in the form of strong oxidants or mild oxidants. In exams, we actually observe the wording strong O in brackets or mild O in brackets to symbolize the reagent that our primary alcohol is exposed to. Now, let's understand that I'm going to do the labeling in the specific example that we have for ethanol. If I have an ethanol molecule and I want to make just the aldehyde, then I can expose my ethanol molecule to a mild oxidant and it will stop at the aldehyde. The aldehyde can undergo further oxidation. It doesn't matter if you use mild or strong oxidant, an aldehyde will lead to a carboxylic acid. We can turn this alcohol molecule straight to the carboxylic acid if we use a strong oxidant on it. If we look more closely at what is happening to our molecule, when we go specifically from alcohol to aldehyde, let's notice that overall what happens is that the carbon that is holding the OH loses one hydrogen. So if I highlight this carbon, that happens to be this one. And we can see that it had two hydrogens and now it has one. Additionally, our oxygen atom loses a hydrogen. So this oxygen atom is this oxygen atom. And in order to make the aldehyde, notice that what happens is that now the carbon and oxygen atom, after each of them lose one hydrogen, it will be double bonded to each other. And that's how we write the aldehyde coming from an alcohol. Next, if I'm going from the aldehyde to the carboxylic acid, all I'm doing is adding an oxygen atom, specifically in between the carbon and hydrogen in my aldehyde. So we can observe that specifically this oxygen atom was placed next to the side where we have the C double bond O connected to H to make the carboxylic acid. So going from aldehyde to carboxylic acid, we see that the only thing that we have to place in our aldehyde to make it a carboxylic acid is going to be specifically an oxygen in between the carbon and the hydrogen that was in the aldehyde. And that's how we do the conversion of the functional groups. Notice that these molecules are not going to change the number of carbons. Now, how do I draw the carboxylic acid from the primary alcohol in the case that my primary alcohol converts into a carboxylic acid? Well, overall, what we observe here is that specifically when we go from alcohol to directly a carboxylic acid because we reacted our primary alcohol with a strong oxidant, what we observe specifically is that the carbon that is holding the OH loses both hydrogens. So we see that these two hydrogens are no longer here. And what we add to this carbon specifically is a double bond to oxygen. And that's how we go from primary alcohol to writing the carboxylic acid. Let's now look at what happens to other types of alcohols when we expose them to oxidants. When we have secondary alcohols only generate ketones. It doesn't matter if we react that secondary alcohol with mild oxidation conditions or strong oxidation conditions. Secondary alcohols can only make ketone, and this is how they are made. We can observe by looking at the example of what happens to 2-propanol that specifically the secondary alcohol is going to lose the hydrogen at the carbon that is holding the OH and the hydrogen that is connected to the oxygen in the OH. So if I highlight my atoms, this is the carbon where the OH is connected to. This is the oxygen in the OH. Let me highlight them in the product. When the carbon atom that is holding the OH loses its hydrogen and the OH group loses its hydrogen, then we have the creation of a double bond between them. And that's why we form a ketone, because now we have a carbonyl group formed. And since it has carbon chains on either side, we can see that they were here in the beginning. That's what forms a ketone. Tertiary alcohols do not react under oxidation conditions, meaning if a tertiary alcohol is exposed to mild or strong oxidant, there is no reaction. Let's do some examples to practice how to predict the products when we have alcohols and they are being oxidized. I'm going to convert each of the following molecules into their skeletal form because when it comes to worksheets and exams, mostly we observe these molecules in skeletal form. The first molecule in its skeletal form is going to be shown as a CH3 connected to a carbon that is also connected to a CH3. That CH group is connected to a CH2 and then it's connected to OH. Remember that we can always convert skeletal to condensed and vice versa. For those students that may have some difficulty into understanding how do I convert this molecule to this one, I'm going to rewrite in the atoms that I have in my skeletal. This is a CH2, this is a CH, this is a CH3, this is a CH3. So if I highlight my atoms, this CH3 is this one. This CH3 is this one. This CH is here. And this CH2 is right here. So you can follow the atoms that we have. And you can see that in the CH2 that is in green is connected to the OH. That molecule is the same one that we have on the first problem on the right. So I'm just going to rewrite the skeletal formula. In the molecule in the bottom, when I write its skeletal form, is going to be a carbon connected to a CH. That CH is connected to another carbon, which is a CH3. Then I'm going to have a carbon connected to OH, and that carbon connected to OH is connected to a CH3. I'm going to do similarly the addition of the atoms. So this is a CH3, this is a CH, this is a CH, this is a CH3, this is a CH3. Let me now highlight the atoms. This CH3 is this one. This other CH3 is this one. This CH is this CH. This CH that is holding the OH is this one. And that is connected to a CH3, which is that one. I'm going to rewrite my skeletal formula on the right side because the molecule is the same. So I'm going to zoom in now to actually write the predict the products. Here, whenever I have an alcohol and I need to determine what is the product of the reaction upon oxidation, I must classify my alcohol. Since the carbon, which is this one, that is holding the OH, is only connected to one carbon chain, this is considered a primary alcohol. When primary alcohols undergo mild oxidation, they will make the functional group called aldehyde. Now, which one of these carbons is the one that is going to form this aldehyde functional group? Is going to be specifically this one. Because overall, in the formation of the aldehyde, what we observe is that one of these two hydrogens is lost, along with the hydrogen in the OH, and then the carbon and the oxygen become double bonded. So how do I draw this? If I go from the point of view of my condensed structure, I will write CH3 connected to CH, connected to CH3. The carbon lost a hydrogen, so it's just a CH. And then I'm going to specifically double bond it to the oxygen because the oxygen in the OH also lost a hydrogen. What if I write it in skeletal form? I'm going to write it on top of the condensed structure that I just wrote. If I do that, then I write the two CH3s that are connected to the CH. Then this CH2 will have a double bond to oxygen and will be connected to hydrogen. Let me just add the highlighted atoms. So this is the carbon that used to be a CH2 and now it's a CH. This is the one that remains as a CH. This is one of the CH3s. This is the other CH3. If I do the same in the condensed, we can see that this is one CH3. This is the other one. This is the CH. And this carbon used to be a CH2, but it lost the hydrogen along with the hydrogen and the oxygen, and that's why is double bonded to oxygen. So that is an aldehyde. We can also write this aldehyde in the following form, just in case if it doesn't appear an aldehyde to your view. This is a double bond O. And let me just extend the hydrogen out. Let me still highlight it in green because it came from that carbon that we had highlighted in green on the left. And that's how we draw the aldehyde coming from that primary alcohol. Let's move on to the second molecule that we have in that first column. Here we have a carbon that is holding the OH and is connected to one carbon chains, two carbon chains. So specifically, this is a secondary alcohol. And when we have a secondary alcohol, the product of the strong oxidation of a secondary alcohol is going to be the formation of a ketone. So how do we draw the ketone? Remember that in a secondary alcohol, pretty much what happens is that the hydrogen that is in the carbon holding the OH is lost, along with the hydrogen in the OH group. And then we're going to introduce a double bond between the carbon and the hydrogen. So here is where the double bond will form. So when I rewrite my molecule, I'm going to first write it in the condensed form. This is going to be a CH3 connected to a CH. That CH is connected to another CH3. This carbon lost its hydrogen and the oxygen lost its hydrogen. Now it's going to be double bonded to oxygen. And then to the right, I have the connection of a CH3. So that's the product of the reaction. If I try to draw it in skeletal form, it will be the following. Let me now highlight the atoms so we're consistent and we can observe where everything comes from. As you can observe, no loss of carbon atoms happen. We only lose hydrogens in this process. If we move to the examples on the right, we can observe that we still have on the top a primary alcohol, and this is a secondary alcohol. Under strong oxidation conditions, the primary alcohol turns into a carboxylic acid. While the secondary alcohol, now under mild oxidation conditions, makes a ketone, just like when we had a strong oxidant. So when it comes to the product for the primary alcohol specifically, how do we draw that carboxylic acid? Remember that overall, what happens is that these two H's are lost, and then we're going to introduce a new bond, specifically a double bond to a brand new oxygen. So when I draw the product in condensed form, I have a CH3 connected to CH, connected to CH3. This area of the molecule is what I wrote here. Then this carbon is what loses the two hydrogens. So I'm just going to write it in. It's going to remain connected to this OH. And now let me just highlight the carbon. This carbon atom who lost the two hydrogens, which is this one, I'm going to double bond it to oxygen, and that's how we form the carboxylic acid. So if I draw it in skeletal form, All I have to do is rewrite my molecule. I'm going to make it smaller. And then the carbon atom, that was the CH2, I double bonded to oxygen. And that's how I write my carboxylic acid. When it comes to the ketone, it is the same product that we wrote right here. So I'm just going to rewrite it. This is a CH3 connected to a CH, connected to a C double bond O, connected to a CH3. It's connected to CH3 right here. Or if I draw it in skeletal form, that's the ketone. Slide 18 has a reaction map for the reactions of alcohols. We can observe that if you have an alcohol, it can actually undergo dehydration. And when it comes to dehydration, the reagent is going to be sulfuric acid. It doesn't matter if you have a primary, secondary, or tertiary alcohols. All of them can undergo dehydration. It depends on the temperature. If you have temperature at 140 degrees Celsius, you will form an ether. While if you have the temperature at 180 degrees Celsius, you will form an alkene. Alcohols can undergo oxidation, but it depends on the type of alcohol. Only primary and secondary alcohols will react. And we can observe that upon oxidation, if you have a primary alcohol, to make just the aldehyde, you need a mild oxidant. If you have a secondary alcohol, it doesn't matter if you use a mild oxidation or a strong oxidation, you can only form a ketone. Aldehydes via oxidation, and that oxidation can be mild or strong, you will only form a carboxylic acid. And lastly, if your molecule has a tertiary alcohol, it doesn't matter if you're exposed to mild oxidation or strong oxidation, there is no reaction. That means that the product of the reaction will be remaining as a tertiary alcohol. Let me write an example. Let's say that I have the following tertiary alcohol and I expose it to strong oxidation conditions. So since there is no reaction, the product of the reaction will be the molecule that I started with because nothing will change.